Good morning, students. Today I am going to discuss with you Bragg's X-ray spectrometer. Before that we had done Bragg's law, then types of X-rays, continuous X-ray, characteristic X-rays. Now we will continue with Bragg's X-ray spectrometer, right? So in this diagram, and this is the Bragg's X-ray spectrometer. Here Coolidge tube is placed from which the X-rays are produced, and these X-rays are passed through fine slits S1 and S2. Then a fine beam of X-ray is allowed to strike on a target which is made of crystal. So we can say generally zinc sulfide crystal, right? And this crystal is placed on a turntable, and it is connected to a ionization chamber through which current is passed, right? And from which we can note down the intensity and current, right? So we'll continue with the working from this diagram. The Bragg's X-ray spectrometer is devised by W.L. Bragg, in which a crystal is used as diffraction grating. The X-ray from the Coolidge tube are allowed to pass through the slits S1 and S2 to get a narrow beam of X-rays. Narrow beam of X-ray is allowed to fall on the crystal D mounted on a turntable of spectrometer, right? The table T can rotate about the vertical axis and its position be read by vernier scale. The intensity of the reflected ray is measured by the current in the ionization chamber, which is attached to the electrometer. Or the reflection intensity is only maximum for those values of theta which satisfies Bragg's law, right? The angle theta is increased in steps, and corresponding values of ionization current is recorded. In this whole arrangement, we can easily calculate the value of wavelength of X-rays, that is lambda. So these are the graph between ionization current and incident angle. As we can see, at specific values of theta, the ionization current sharply or abruptly increases, and it makes peaks at these values of theta. And another graph is between intensity and incident angle. Here at specific incident angle theta 1, theta 2, theta t, the intensity is maximum. Intensity shows peak values, right? So these are the graph between ionization current and incident angle, and intensity versus incident angle, right? So next topic is X-ray radiography. So these are X-ray waves, these are electromagnetic waves having wavelength between 0.1 angstrom to 0.5 angstrom. When X-rays penetrate through the component, they are absorbed by the component. They are passed through test piece and falls on a photographic film. The voids and cracks and you can say defects in the test piece allow large intensity of X-rays to pass through them, right? The large intensity radiations that fall on film form more dark areas on it, and low intensity area appear transparent after developing the film. The image of the defect areas as dark region, right? So we can indicate, we can conclude from this that where there is a dark region, there is a defect in the, that is a defect in the dark piece. So applications, X-rays have medical applications to make photograph of the interior of the body, to detect fracture and to destroy tumors, we can say, right? Thank you very much.